Good evening, sir. This is Masiko Ian, and I will be taking you through what we have done so far concerning our final year project. So I'll start by taking you briefly through what our data looked like after we had just acquired it, and then what it looked like after we performed the EDA. I'll also show you some of the how we performed the exploratory data analysis and the SMOT and smooth analysis. Then the machine learning models in Colab and their outputs. Then lastly, I'll take you through the amino acid analyzer, its code and its output. So to start with, so this is what our data looked like before, after we had just acquired it. Escherichia is very highly represented under the bacteria because Escherichia has different types. You've heard about E. coli, we have E. coli, E. coli, yeah, and others. Yeah, but later on, as the model does the training and the amino acid analyzer does what it does, it differentiates these different types. Now, here under the antibiotics, we have many sequences conferring resistance to clarithromycin, but this was intentional by CAD. It's explained under in the documentation accompanying the dataset because it's because clarithromycin is unique in a way that its sequences, the way they appear, their patterns also indicate can also work for other different sequences, other different resistances to other antibiotics. Yes, so quickly into the EDA. So this is our EDA code. So we started by when here the unique library is RE, the one for regular expressions, because we need a regular expression to be able to pass the faster files and extract the sequence names from the header files. Then additionally, we had to set a minimum sample threshold. So any antibiotic that had less than 5 sequences representing it was dropped. Then since we are going to do augmentation, we set an augmentation target to 500, and then mutation rate 0.002. This one is to help with the augmentation because and for sequence augmentation we are just generating random A's, T's, C's and G's, but making sure that even the random ones we've generated, when tested, they still confer resistance to the same antibiotic and represent the same microorganism. And then synthetic ratio, we had to make sure that it's 0.3. This was done to ensure that it doesn't go beyond 30%, so that the original sequences take up 70%. This would keep us from biasing the model with the new sequences. Yes, so here this is basic file selection because when the user runs this executable file, they get a pop-up to select the file path they're interested in. That's why we imported tkinter. And then so here we tried to pass the faster file, and so that our regular expression tells the program to read through the headers. So header files start with this greater sign. uh, if it does not start with a greater sign, then it's a sequence. That's how generally faster files for sequences are structured. So this EDA model can work on any antibiotic sequence as long as it's headed the same way. We just need to change around here because some of them may not show this statement conferring resistance to. But for us, we had to go through and sort and make sure that before the antibiotic name appears, we have conferring resistance to, which is what the regular expression checks for. And this is the space character, then appends other words after it. Then we loaded the data and then filtered out the rare cases using the minimum sample threshold and dropped the ones that had less than 5 sequences. Then we performed augmentation. Since we only have 80 C and G, we are trying to generate random sequences using the 80 C and Gs. But here we are these lines of code trying to make sure, plus the mutation rate is to help us make sure that even the random sequences that are generated are related to the original ones we have. Yeah, so we performed the augmentation, and then the sequences were stored in a different FASTA file, and then they were visualized. So quickly to the visualizations. Yeah, so this is what our data looked like originally. Now, this one is after filtering out the classes that had less than 5 sequences. And then here, this is after augmentation and unifying them all up to 500. Yeah, so clarithromycin also help to get some of them to, so it would pick out matches that are most related to a particular antibiotic, and try to append them into those, and then the gaps that were left were covered up by the augmentation process. Yeah, so this one is for sequence length. So generally, most of our sequences, actually our longest sequence has around 3100 nucleotides, and the minimum has around 1500. So this one basically represents the sequence length. Yes, and then this is the file that has augmented sequences. So since we are interested in the antibiotic name and the words conferring resistance, so that it's able to be read by the machine learning models, we this is how our new sequences looked like. So they still make sense. So macrolide antibiotics, and here we have erythromycin, and so on. Yes, so now that we are done with the EDA, let me take you through the machine learning models. So um, let us start with like we had earlier agreed with you, we were supposed to train a long short-term memory network alone, then train a recurrent neural network alone, then combine the LSTM with the RNN, then finally create a model that combines all of them and passes them into a meta learner to see how predictions were made and help other future predictions. And some of them used KEMA encoding, but later on KEMA encoding was dropped, as you'll see later on. So first of all, this is our LSTM, independent LSTM, long short-term memory. Um, yeah, so our long short-term memory starts by installing dependencies, and most of them were already available since we had used Colab to train other models. Other other models that didn't perform as we initially wanted, but we extracted out ones that had good levels of accuracy, F1 scores, and recall. Yeah, so we went ahead to do, yeah, so here it loads the data, it passes the FASTA files, and then goes ahead to process them. So here you notice that we don't, under antibiotic, we don't have antibiotic name, which eventually gave us issues. It led to overfitting somehow, somewhere. Yeah, so ATCG were represented by 1, 2, 3, and 4 respectively. This turning them into integers helped with the explainability bit, because most algorithms like SHARP only detect either binary or integer data. Yeah, so we went ahead and did data splitting. Initially, we had not split our data initially into training and validation and testing sets, but the model was true was the model was programmed to be able to read these to and perform the data splitting. So after splitting, we have these in our training, validation, and testing sets. Yeah, so here this basically shows the iterations that the LSTM had to go through. These are the different layers: the embedding layer, the dense and the dropout layers, then the bidirectional layer. Yes, so all our parameters were trainable, which we were not getting in the previous ones that we trained and gave us low accuracy. Some were dropped. Yeah, so then memory aware training. Yeah, so we ran our epochs and finally attained these matrices. This is the plot. Then now explainability. Here we used Lime Tabular, and yeah, these are our matrices. But like I said on top, the model was not able to clearly extract the names of the antibiotics. So we have some overfitting. You can see these recall values and precision values are quite interesting, quite insane. Yeah, so that was model number one, though we dropped others before that. But from the ones that gave us promising results, this was the first one. And yeah, so moving on to the other one before we go to the most perfect one. Now, this was a combination of an LSTM with with the with the KEMA encoding. Here the interesting bit is the KEMA encoding. So data passing is done as we had done before, and here we tried to make sure that sequences are read the way they are. And so here we can see the sequence is given, then antibiotics, Campylobacter jejuni. So these are they're only showing us a few, but you can see we loaded over 14,000 sequences. Then KEMA encoding is the K value of 19. If you count this, they're actually 19. But then that gave us challenges, as you later on see. So after doing KEMA encoding and feature engineering, we had 315,930 features. Then we did target encoding for particular antibiotics and microorganisms. And so we built the LSTM. These are its layers. Yeah, so now the challenge came here, where we realized that to try to run all these epochs, every epoch would need about 3 hours, because with KEMA encoding, we had a lot of representations. So we eventually decided to drop KEMA encoding for these models, and we used it mostly in the Amino Acid Analyzer. Yes, so moving on to the last model, the one that performed best, and also embeds all our three different algorithms, the LSTM, the RNN, and goes ahead to do passing into the meta learner. It's loading. Yeah, so here we are. It does data loading as usual. Then it went ahead to read the FASTA files. And so here we only focused on the sequences that only have antibiotic specific sequences, because the goal eventually is for us to be able to give it a sequence, and it tells us that this sequence you've given me, because of ABC, it is going to show resistance to a particular antibiotic. So we realized at this stage we did not need the sequences whose overrepresentation leads to antimicrobial drug resistance. So we loaded 2,403 sequences for the different antibiotics. So now here the passing was done accurately, because we were able to extract out the actual antibiotic names. So this was initially before any EDA was done on the data. Yes, so we did Markov clustering, Markov-Seaborn clustering, and yeah, so and now faster passing again from this data set. And then we did augmentation up there, but we had to redraw these graphs in the EDA code I showed, because as you can see from here, the labels, the graph labels, are kind of clustered together. But yeah, it was able to do its own EDA, and this was after augmentation. and now sequence length after augmentation. Then yeah, so we generated heat maps to for the data representations. Interest is in this one. Yeah, so here this was before after augmentation, before augmentation, and this is the whole thing merged together. Sorry, yeah, this one, because it shows before and after. Yeah, so here the pattern it used was doubling the sequences. So before, if we had 36, here we have 72, but then we had to drop these very big ones and use them the way they were. Then yeah, so our longest sequence had 3140 nucleotides. Yeah, this was the shape of our encoded data. Then we did training, and this our LSTM was designed in such a way that it can, as it does what it does, it shows us the sequences and the layers it's going through. So this is the representation. It will be embedded in the report. And yeah, now here, this is the actual training. These are our metrics. Yeah, then afterwards, since we wanted to pass the RNN and the LSTM into the meta learner, we had to package it and save the model first, and then we went ahead and passed everything into a meta learner. Loading. Yeah, now here, this is the meta learner training. Yeah, training on the LSTM features. The meta learner uses a random forest classifier together with TensorFlow. Though TensorFlow was imported mainly because we wanted to use TF explain, since for it does not specify that the data has to be numerical or binary. Yeah, so yeah, the meta learner was trained very well, and it extracted the most important features, 10 most important features, and these are plots of the 10 most important features, and they are labeled as follows: 10997 for the different sequences. Yeah, so like I said earlier, clarithromycin is highly represented because its sequences can be used interchangeably by other antibiotics. Yeah, so we had a small error with the explainability bit, but then we went ahead and so wait a minute. Mm, so this is sharp, which gave us some small trouble, but yeah, we had to import a dictionary to help us generate a simple report that can guide decision making. So this is some CSS and HTML. Yeah, so this is what our small clinical report looks like. Also for explainability level, for help with explainability. So it predicts a sequence and gives a value. Then it goes ahead and gives a clinical recommendation to the medical worker: avoid this antibiotic and consider alternatives for a given sequence. It gives you alternatives especially according to the molecular basis. So viomycin, kanamycin, and amikacin can be used in place of capreomycin. Yeah, so those were our machine learning models. Now, lastly, I'm going to briefly take you through our acid analyzer. So this amino acid analyzer was divided into two sections of code. So the first one gives us summaries of the antibiotics, all of them. Like if it's erythromycin, it doesn't go specifically into each microorganism presenting resistance to erythromycin, but it summarizes all erythromycin resistance sequences and goes ahead to give explanation. So we manually typed the dictionaries for the different antibiotics and the explanations. This will later on be of help in the PDF that is generated by the amino acid analyzer. Since it's not a direct machine learning model, we had to develop our own manual explainability technique so that it makes sense and it doesn't keep whoever is trying to to make sense of the data in a black box. Yes, so here this is basic file parsing, since they are faster files. Yeah, so sequences are loaded, camera encoding is done, and then these explanations are to help with generating the PDF report. These are just styles for styling the report, and yes, so then the graphs. So the output of this, it's a Python executable file. I've already sent invitations to our GitHub code. It shows, so the file on the GitHub repository has all this here, even the models we trained in Colab. Yes, so hmm, yes, so this one is the one that summarizes the antibiotics. So it generates the graphs. You can see the graphs are fewer, but now they focus on. So this one they focus on particular antibiotics, amoxicillin. They don't extract out. You see that you spot the difference when we go to the second option. Then it generates a PDF report. So the PDF report starts by showing us provomycin. It shows us the given antibiotic and explains what is likely to occur most, and then we go ahead to look at what is overrepresented, and then the ones that are highly represented, the ones that appear dominantly, are explained as to why they are explained according to their role in resistance to that given antibiotic. So every one of the graphs we had has its explanations in this PDF report. Then it also goes ahead to extract a CSV file that can be read in Excel, showing percentages and counts, and the different amino acids and the antibiotics. So Kemba encoding, we limit for this part. We limit the K value to 3 because amino acids have only 3 nucleotides. Yes. So now these are the frequencies, and then to make more sense, they are plotted. Then the second part is this one extracts out amino acids per. It extracts out microorganisms according to the antibiotics they confer resistance to. So if it's E. coli conferring resistance to pulvomycin, it will also have another graph for E. coli conferring resistance to ampicillin, and so on. So the only change we had to make was in the KEMA encoding, because here, instead of the previous one only focuses um KEMA encoding. Yeah, so the previous one, here, as it extracts the antibiotic, it just extracts the plain antibiotic name without splitting it. So here, because we go ahead to split between the antibiotic name and the microorganism name, which helps us to classify the specific sequences we are interested in. And then its output, according to, now this is its output. Now you can see from its representations, first of all, it has much more graphs. Sorry about that. But yeah, so it has smaller representations, but so each one has fewer since it's not a summary, and its PDF report looks a little different. Yeah, so now you see it's very specific. It shows E. coli mutations conferring resistance to provomycin in particular. Later on, we'll see E. coli conferring resistance to something else, and we also see a different microorganism conferring resistance to provomycin, and so on. And then the explanations, because we had dictionaries appended into the code, we have specific explanations for each one of our graphs. Yes, so what we wanted to know initially, why we wanted to reach out today, was to understand how because these graphs and all these documentations are essential for the final output. We wanted to know we would be able to merge them into the final report. Yeah, so for now that is it. Thank you very much for your time.